Okay, the purpose of this video is to provide a brief introduction to feedback control. I will assume at this point that you already understand the concepts of a transfer function and how to work with systems in the Laplace transform domain. So the basic context here is that quite often we have a system that has input and an output. And we can't actually mess with what's internal to the system. We call this the plant. For example, the input, if you think about the idea of a steel mill, where you take red-hot slabs of steel and run them through rollers, and the idea is to get the output slab of steel to be the right thickness. So the rollers smash it down until it's the right thickness. So there the input might be the force on the rollers, or maybe an electrical signal which then gets turned by hydraulic equipment into force or something like that. And the output might be the thickness of the steel that's running out of the plant. Okay, so that's actually why we call this a plant, is that quite often we use industrial control sorts of situations here. It could also be that the plant is the drive system of a car, and if you're building a cruise control, then the input might be the throttle setting, and the output might be the speed. So we talk about any system that we want to control as the plant, even though sometimes that doesn't make a lot of sense. So our goal is to get the output of the system to do something that we want it to do, but quite often we can't mess with something internal to the plant, so we add a control system. The way the control system works is that we have a desired value. It goes into our control system. The output of the desired value goes into the plant, or I'm sorry, the output of the control system, and the output of the plant gets fed back into the control system. So the idea is that okay, I'm sorry for that awkward pause. I just had to give guidance to a student. So anyway, we have the control system providing the proper input to the plant, and the plant output is then fed back into the control system so it can look at what's coming out of the system, look at the desired value, and make the changes that it needs to make. So if we provide a little more definition to this model, this isn't the only way that it can be done, but this is one way that it can be done, we'll provide a little more definition, and we'll also define some notation here. So we'll make this stuff go away. And we'll change colors just for interest. Okay, so here I have my desired value, and I'll call this x. Okay, and all of these things are going to be in the Laplace domain, so this is x of s. And from the desired value, I'm going to subtract a value that for right now you can think of as the output of the system, although in just a second it's going to turn out to not be exactly the output of the system. And so the thing that comes out of here is the error. Okay, this is the difference between what we want, the desired, and what we think we're getting out of the system. We take that error and we run it through a controller, and the controller gives us an input to the system, or to the plant, which we're going to call u. Now this is potentially confusing in the sense that the input to a plant is oftentimes called u. We have also defined a unit step function. Hopefully we'll be able to keep those straight. So we then have the plant, and the output of the plant, which we'll call y. we take the output of the plant and we bring it back through possibly some sort of sensor here. And the idea is that sometimes we can't observe the thickness of the iron coming out of the roller directly. We have to measure it. And when we measure it, there may be errors involved. It may take the sensor time to settle down to a correct measurement. So the idea then is that the sensor gives us something that we'll call y hat, which is in some sense our best guess about what the output of the plant is. Now, if we know exactly what's coming out of the plant, then we'll just set the transfer function of the sensor to be equal to 1, because that means that whatever comes out of the plant just goes into our controller that's determining error. We'll assume that the controller has a transfer function gc of s. We'll call the transfer function of the plant p of s, and we'll call the transfer function of the sensor g of s. Okay, so we have all of these things, and I should point out all of these are defined in terms of the Laplace transform, so these are all functions of s. And now we'd like to figure out the relationship between x of s, our desired value, and y of s, our output of the plant, in terms of all these, the transfer function of the controller, the transfer function of the plant, and the transfer function of the sensor. To do that, we'll use a trick. This looks really daunting until you've actually seen it done the first time, and after that, hopefully it'll look sort of trivial. And what we're going to do is we'll start with the output and work our way back through the chain of subsystems that we have through the plant, then the controller, the error calculation, and then the sensor. And we'll end up then with an equation that relates y of s, which is the output of the system, to x of s, which is the desired input. Well, it's the input that the desired value that we input to the system. And from that we can get the transfer function of this overall control system. So and I'm going to go through this fairly quickly because I don't want to waste a whole bunch of your time with it. Okay, so y of s is given by the transfer function of the plant times the input to the plant. Okay, so the input to the plant, u of s, this guy right here, well, the input to the plant is given by the transfer function of the controller times the error signal. Okay. And the error signal, see how many times we can change colors in one equation. This error signal is given by, this guy here is given as the desired value minus the estimate of the plant output. Okay. And finally, the estimate of the plant output. Okay, so we'll rewrite this all one more time. Now this is a lot of work to go to, but the colors are so beautiful that we have to do it this way. Okay, so we'll finish up with a hot pink here. So y hat of s is equal to gs of s times y of s. Okay, so what we have here is y of s on this side. We have another y of s over here. We have x of s. And everything else is a transfer function of one of the components, or one of the subsystems, PS, GCS, and GSS. So what we need to do now is solve this equation for y of s. And we can do that by noticing that we have P of s times G sub c times G sub s times y of s. taking that term and moving it over to the right or to the left-hand side of the equation, leaving this P of S, G sub C of S times X of S on the right-hand side. And when we do that, let's see, we get Y of S plus PSGC of S, GS of S, Y of S is equal to PC GC X. Okay, so we have a Y, this Y here, and this Y here, which we can factor out. We have an X, and I'll, make everything go away. This is bad. I've just revealed that I've been looking at Wikipedia to figure out how some of this stuff works. You no longer respect me as an independent academic. Okay, so now we've got this formula. I'm going to skip a couple of steps, but we have Y of S over X of S, which again is the transfer function of this overall system. That's PC G sub C over 1 plus, that should be P sub S. I have no idea what happened there. 1 plus P of S, GC of S, GS of S. And there you have it. We have the overall transfer function in terms of the transfer functions of the different blocks that we've been looking at. So I think we'll stop this video here. We'll do one more video that has a very simple example to show you how the control system can change things. And then after that video, we may actually do many more, depending on how much stuff we need to convey.